Today we're going to talk about quantitatively potential energy diagrams, and we are going to look at this diagram in the forward and the reverse direction. Okay, so let's do a little review. Here's my potential energy on this side, and you can have time down here, or sometimes you'll see the words reaction coordinate. And we have our reactants here and our products down here. And this right here on top is our activated complex. Remember, that's when our reactants are breaking bonds and forming bonds, and it's kind of that in between till we get to the products. Okay, so it doesn't matter which way we look at it, forward or reverse, our potential energy of our reactants is 200 kilojoules. I have kilojoules down here. Our products are at 100 kilojoules, and our activated complex has a potential energy of 300 kilojoules. Okay, now why are we going to look at it both ways? Well, in our next unit, we're going to talk about equilibrium, and we can force reactions to go forward or backwards. And if we're running backwards, that means our products are now our reactants, and they're turning into products this way. So we're going to take our products, they're going to rearrange and go back into reactants. So that's why we're looking at it in both directions. Okay, now enthalpy is the heat of reaction, and sometimes you'll see it as delta E. That's just a generic term for energy, and this is always the difference between the products and the reactants. Okay, so if I make a little dotted line between here and between here, my difference here would be my enthalpy. That would be my delta H. Okay, it doesn't matter if I'm going forward or reverse, the number's the same. But as you'll see, our signs change. So let's first look at our forward reaction. If I go forward, my reactants are higher than my products, so I'm going downhill. I have to release energy. That means it's exothermic. Okay? And what does that mean about my delta H? It means my delta H is going to be negative. And how big is my delta H? Well, that's between 100 and 200. So that would be negative 100 kilojoules are being released from this reaction. Now, the activation energy is the size of the hill. It's how much energy I need to put in before my reaction can start going on its own. Okay, so here's my reactants. Here's the hill. So if I'm going forward, this is going to be my activation energy, and I'm going to put a little FW there for forward, and that is between 200 and 300. So that is 100 kilojoules. Okay, so again, activation energy, let's make that a little clearer. Activation energy forward, so going this way, it's the hill I have to run up. Okay, now let's look at it going backwards. Let's say I'm running this reaction backwards. First of all, if I go backwards, my starting is lower than my ending. Okay, so I have to go uphill now going backwards. That makes the reverse direction endothermic. And that means I have a positive delta H. So what is my delta H? It's between the products and the reactants, so that is 100. Notice, my delta H doesn't change because it doesn't matter which way I go. It's always between products and reactants. And the only thing that does change is the sign. So if it's exothermic, I need that negative in front of it. If it's endothermic, I need the positive. So activation energy going in the reverse direction. Again, the activation energy is always the hill. So my hill starts down here and goes all the way up to here. So this is a much bigger hill. So this is my activation energy reverse, okay, going that way. And I have that between 100 and 300, so my activation energy reverse is 200 kilojoules. Okay, so now the other thing that we should look at is which way is going to be faster, running the reaction in the forward direction or the reverse direction? Well, the analogy is, which hill can you run up faster? You can run up the shorter hill faster, so forward direction is the smaller hill, and that is the way that's going to be faster.